Welcome to the Manufacturing Lithium-Ion Batteries, a practical introduction course. Today, we're continuing Chapter 4, which moves into the core of this program, the lithium-ion battery manufacturing process. In this session, we'll walk through the foundation of the manufacturing process with a full schematic overview. Let's get started. Learning objectives. This session provides a high-level view of the full lithium-ion battery manufacturing chain, from individual cell production to module and pack assembly. Our goal is to help you understand how all major processes fit together, and how today's large-scale factories are organized to support mass production. By the end of this module, you should be able to 1. Describe the overall flow of LIB cell and module manufacturing. 2. Recognize the typical layout of a modern LIB production plant and understand why processes are arranged in a specific order. The images show the Blue Oval SK plant in Kentucky, where commercial production has recently begun. It represents a practical example of a state-of-the-art manufacturing environment, highly automated, tightly controlled, and designed to support large EV programs such as the Ford F-150 Lightning and E-Transit. This illustrates the scale, cleanliness, and precision required to operate a competitive LIB facility in the United States. Terminology slide. In this course, you will encounter many new technical terms used throughout the lithium-ion battery manufacturing process. These terms describe materials, components, and key steps that recur throughout the entire production flow. Among them, two concepts are especially important to highlight early: cathode active materials, CAM, or the core functional materials in the cathode, such as NMC, NCA, and LFP. They determine much of a battery's energy density, performance, and cost. The solid electrolyte interface, SEI, is a thin, protective layer formed on the anode during the first charge cycle. A stable SEI is essential because it allows lithium ions to pass while preventing unwanted side reactions, directly influencing safety and cycle life. As we progress through the training, you will gain a clear understanding of how these terms connect to real manufacturing steps and to the performance of finished battery cells. Lithium-ion battery manufacturing process flow. This diagram illustrates the full production flow of a lithium-ion battery, from raw materials to the final battery pack. Rather than covering each individual box, it is important to recognize that the entire process is organized into four major stages. 1. Electrode manufacturing, where active materials are mixed, coated, dried, pressed, and cut to form anode and cathode electrodes. 2. Cell assembly, where electrodes, separator, electrolyte, and the housing come together to form a sealed cell. 3. Formation and testing, where the SEI layer is created, and the cell is stabilized, tested, and graded. 4. Module and pack assembly, where finished cells are combined into modules and packs with electrical, thermal, and safety systems. I encourage you to take a moment to carefully study the flow diagram. Understanding how these steps are connected will help you visualize the entire manufacturing sequence as we explore each process in more detail throughout this training. Overview: Manufacturing Li-ion battery pouch type. This slide presents a complete, step-by-step process flow for manufacturing pouch-type lithium-ion cells, organized into four major stages. 1. Electrode manufacturing. 2. Cell assembly. 3. Formation/aging/cell finishing. 4. Module and pack processes. The table lists 26 detailed sub-steps, from raw material preparation and slurry mixing to final sealing, formation cycling, inspection, and packaging. These steps highlight how pouch cells are built layer by layer: coating anode/cathode sheets, stacking with separators, injecting electrolyte, sealing the pouch, and completing formation. Two diagrams on the slide visually illustrate the internal structure of a pouch cell, showing how the anode, separator, and cathode layers are stacked and enclosed in the pouch film. Please note that this slide is the first of 3 detailed process tables. The following slides will show cylindrical and prismatic cell manufacturing flows. I encourage you to compare all 3 tables carefully to observe how the electrode steps are similar across cell types, while the assembly and sealing processes differ significantly due to the unique cell formats. Overview: Manufacturing Li-ion battery, cylindrical type. This slide continues from the previous pouch cell overview and presents the full manufacturing flow for cylindrical cells, using the same four major process groups: electrode manufacturing, cell assembly, formation/aging, and module/pack. For cylindrical cells, the electrode fabrication steps, 1 to 6, are identical to pouch and prismatic formats. The key differences appear in the assembly stage, where the electrode sheets are wound into a jelly roll with careful tension control, inserted into a metal can, laser or mechanically sealed, and filled with electrolyte through a vent. Formation, aging, final testing, and pack level steps are the same across all cell types. The images help visualize the internal structure of a cylindrical cell, showing how the jelly roll, separator, electrodes, and safety components are arranged inside the can. Ask trainees to compare this cylindrical table with the pouch version shown earlier, noting where the processes converge, electrode manufacturing and formation, and where they diverge, assembly and sealing methods. Overview: Manufacturing Li-ion battery, prismatic type. This slide presents the prismatic cell manufacturing workflow, structured in the same four major stages you saw earlier: electrode manufacturing, cell assembly, formation/aging, and module/pack. The table lists the detailed steps for prismatic cells, which share the same electrode-making sequence as pouch and cylindrical cells. The key differences appear in the assembly stage, where prismatic electrodes are sheet-stacked or Z-folded and inserted into a rigid metal case, followed by header welding and vacuum electrolyte filling. Prismatic cells require careful tab bus welding, case sealing, and moisture-controlled handling, since the rigid casing design influences thermal behavior, mechanical stability, and safety venting. After assembly, the cells move through the standard formation, aging, grading, and packaging steps common to all formats. Two images are included to help visualize the internal structure of a prismatic cell and its external form factor. Please review this table alongside the pouch and cylindrical versions shown previously. Comparing the three formats will help you clearly understand how assembly methods diverge while the early and late processes remain largely consistent across all cell types. Overview: Surge of battery production. This slide highlights the rapid global expansion of lithium-ion battery manufacturing capacity. The three factory images, Tesla's Gigafactory in Nevada, SK Battery America in Georgia, and LG Energy Solution in Poland, illustrate how major companies across the US, Europe, and Asia are scaling up production to meet EV demand and strengthen regional supply chains. The chart on the right shows the broader trend. Global battery cell production capacity is projected to more than quadruple from 2020 to 2030. China continues to lead, but significant growth is also occurring in Europe and the United States, driven by aggressive EV policies, domestic supply chain strategies, and massive private investments. Together, the images and data emphasize the industry's global acceleration and the strategic importance of battery manufacturing in the transition to electric mobility. Overview: Manufacturing Li-ion battery. This slide introduces the four major stages of lithium-ion battery manufacturing: electrode production, cell assembly, formation, and pack/module assembly. Each stage builds on the previous one, from mixing and coating raw materials into electrodes, to assembling the cell structure, to activating the cell through formation and aging, and finally integrating cells into modules and packs. The visual diagram on the right illustrates these steps for both cylindrical type and pouch type batteries. While the exact methods differ slightly between cell formats, the overall workflow remains consistent across all lithium-ion technologies. As we move forward, we will explore each stage in more detail so you can understand how materials become a finished, functional battery system. Overview: Manufacturing Li-ion battery, Step 1. This slide introduces the first major step in battery production, electrode manufacturing. At this stage, the cathode and anode are created through four key subprocesses. First, active materials, binders, and additives are mixed with a solvent to form a uniform slurry. Next, the slurry is coated onto metal foils, aluminum for the cathode and copper for the anode. The coated films are then roll-pressed to achieve the required density and smoothness, which improves lithium-ion transport. Finally, the electrodes are slit and notched into precise shapes to prepare them for the cell assembly stage. These steps establish the foundation for the battery's performance, safety, and consistency. Overview: Manufacturing Li-ion battery. Step 2, 1/2 cell assembly, pouch-type cells. This slide explains the second major step of manufacturing, cell assembly, where electrodes and other components are combined to form the actual battery cell. The assembly process differs by cell format, pouch, cylindrical, or prismatic, but the underlying goal is the same: to stack or wind the electrode layers and introduce electrolyte. Here, we focus on pouch-type cells. A multi-layer pouch film is shaped to form pockets that will hold the electrode stack and the electrolyte. Inside this pouch, the cathode, anode, and separator layers are stacked through a lamination and stacking method. After stacking, electrolyte is injected so it can fully penetrate the porous structure of the electrodes. The result is a sealed pouch cell that will progress to formation and aging. The images help visualize how a pouch cell becomes part of a module and ultimately a pack. Overview: Manufacturing Li-ion battery. Step 2, 2/2 cell assembly, cylindrical type cells. This slide introduces how cylindrical cells are assembled, which differs from the winding method used in pouch cells. In this approach, the cathode, anode, and separator are rolled together into a tightly wound jelly roll, which is then inserted into a metal can. Tabs made of aluminum, cathode, and copper, anode, are connected before the electrolyte is injected. After sealing and adding insulation, the cell assumes its familiar cylindrical shape. The images illustrate the evolution of cylindrical formats, such as Tesla's shift from 18650 to 2170 and now 4680, and how individual cylindrical cells are organized into modules and then full battery packs. This helps trainees visualize how the cell assembly step ultimately integrates into the larger pack system. Overview: Different LIB cell formats. This slide introduces the 4 major lithium-ion cell formats: button, cylindrical, prismatic, and pouch. Each format has a different structure, level of energy density, and manufacturing approach, which is why different industries choose different cell types. Small button cells are used in low-power electronics, while cylindrical cells remain popular for tools and EVs due to their durability and ease of production. Prismatic and pouch cells offer higher packaging efficiency and flexibility for modern consumer electronics and electric vehicles. As we move forward in the course, understanding these form factors will help you see why manufacturing steps diverge depending on the cell type. Overview: Manufacturing Li-ion battery. Step 3, Formation. In this step, we move into one of the most important phases of battery manufacturing: formation. This is where each cell is essentially brought to life. After the electrolyte is filled, the cell is allowed to rest at room temperature. During this period, called aging, the electrolyte slowly wets and penetrates the electrode's internal structure, preparing the cell for controlled charging. Once the wetting is sufficient, the cell begins a series of slow and carefully managed charge-discharge cycles. These early cycles are critical because they create the SEI layer on the anode, a protective interface that ensures stable long-term operation. As this layer forms, the cell also demonstrates how well it handles lithium-ion movement under real operating conditions. For pouch-type cells, these initial cycles often generate small amounts of gas. Before the process continues, this gas is removed through a degassing step, after which the cell is resealed. The formation and aging cycles continue until the cell reaches stable performance, and any substandard cells are screened out during the final checks. Formation takes time, but it is essential. It is during this stage that a lithium-ion cell becomes a reliable, safe energy device ready for integration into a module and eventually a battery pack. Overview: manufacturing Li-ion battery, Step 4 pack process. In the final step of cell manufacturing, we transition from individual cells to a functional, application-ready battery pack. This is where everything comes together. Once the cells have passed all electrical and safety checks, they are arranged side by side and mechanically fixed inside a module case. Here, the cells are electrically connected, either in series, parallel, or a combination of both, depending on the voltage and capacity required by the application. When the module structure is secured with its cover, it becomes a solid building block for the pack. These completed modules are then placed into a battery pack enclosure, where additional components, such as wiring harnesses, bus bars, cooling systems, and protective devices, are integrated. Finally, the battery management system, BMS, is applied. The BMS monitors voltage, temperature, state of charge, and overall health, ensuring safe and optimized operation throughout the battery's life. By the end of this step, the battery pack is fully assembled and ready for installation in an EV or energy storage system, completing the journey from raw materials to a fully functional energy solution. Step 1, Electrode Manufacturing, Part 1 of 4 for mixing. In this first step of battery manufacturing, we begin making the cathode and anode. Electrode manufacturing is a chain of processes that includes mixing, coating, roll pressing, and finally slitting and notching. On this slide, we focus on the mixing stage. Here, the raw powders for the cathode and anode are carefully measured and combined with solvent to create a slurry. Binders are added so that the particles will adhere well to each other and to the metal foil later. Conductive additives are then mixed in to create continuous electron pathways through the electrode. The goal of this step is a homogeneous, stable slurry with the right viscosity and dispersion, because any non-uniformity here will directly affect coating quality and, eventually, the cell's performance and lifetime. Step 1, Electrode Manufacturing, Part 2 of 4 for coating. In this slide, we focus on coating, where the mixed slurries are transferred onto the metal current collectors. Cathode slurry is coated onto aluminum foil and anode slurry onto copper foil, typically using a slot die coater. After coating, the electrodes pass through a drying oven, usually above 100 degrees Celsius, to remove solvent and fix the active material, binder, and conductive additives onto the foil. Advanced lines may use double-layer slot die coating, which can apply 2 different slurry layers in a single pass. This helps tailor the top and bottom of the electrode for better ion transport and mechanical strength, while also improving line speed and cost efficiency. Overall, this coating step converts liquid slurries into solid, functional electrode films ready for densification in the next stage, roll pressing. Step 1, Electrode Manufacturing, Part 3 of 4 for roll pressing. In this third part of Step 1, we focus on roll pressing the coated electrodes. After drying, the electrode sheets are fed between 2 large rolls and are evenly flattened. This compression makes the coating thinner and increases its density, which means the active particles are packed more tightly and are better connected to each other and to the current collector. A well-calendared electrode provides smoother pathways for lithium ions and electrons to move, so internal resistance is lower, and battery power and energy output improve. The target density is carefully controlled because it determines how well the materials are pressed and directly influences cycle life, rate capability, and safety. Step 1, Electrode Manufacturing, Part 4 of 4 for slitting and notching. In this final electrode manufacturing slide, we look at slitting and notching, where the long, rolled electrodes are cut to the exact size needed for the cells. First, the wide electrode sheet is slit vertically into narrower strips to fit the cell format. Next, in the notching step, a V-shaped cut and tab areas are formed. Here, the machine removes the uncoated regions of foil while leaving clean corners where the current collecting tabs will later be welded. These cutting operations look simple, but edge quality is critical. Poor slitting or notching can create burrs, particles, or dimensional errors that increase resistance or even lead to internal short circuits. So this step is where we turn a continuous electrode roll into precise, cell-ready pieces with controlled geometry and clean edges. Step 2. Cell assembly for pouch cells. Slide 1 of 2 pouch cells are light and highly energy-dense battery forms. In this slide, we look more closely at how a pouch cell is built. First, in making a pouch case, a multi-layer polymer, aluminum film is pressed over a mold to create 2 pockets, one for the electrode stack and one small air pocket that can temporarily hold gas. This flexible pouch will eventually replace the rigid can used in cylindrical and prismatic cells, helping reduce weight and improve energy density. Next, in making a bicell, we assemble the basic electrochemical unit of the pouch battery. Multiple cathode and anode sheets are stacked with separators in between to create a laminated structure, typically in the sequence cathode/separator/anode/separator and so on, so that the same electrode type appears on both outer faces. This bicell stack will later be extended, laminated further, and combined with electrolyte to form a complete pouch cell. Step 2. Cell assembly for pouch cells. Slide 2 of 2 in this slide, we continue the pouch cell assembly we started on the previous page. After the pouch case and bicell are prepared, we move into lamination and stacking. Half cells made of anode and separator are laminated onto the bicell, while additional cathode layers are stacked on the opposite side of the separator. By repeating this sequence, we tightly pack many electrode layers into the pouch, which increases energy density while still keeping the structure mechanically stable. Once the stack is complete, we perform electrolyte injection. Electrolyte is introduced into the air pocket and allowed to penetrate all the pores of the electrode stack. Any remaining gas in this pocket will be removed later during the degassing step. At this point, the pouch cell has its final internal structure and is ready for formation and aging. Step 2. Cell assembly for cylindrical cells. Slide 1 of 2 in this step, we look at how cylindrical cells are built using the winding method. Cathode, anode, and 2 separator films are fed into a winder and wrapped together around a mandrel, creating the familiar jelly roll structure that fits inside a cylindrical can. Once this jelly roll is formed, we move to tab welding. An aluminum tab is welded to the uncoated cathode edge and a copper tab to the uncoated anode edge. These tabs will later connect the jelly roll electrically to the can and to the external terminals, completing the basic internal structure of a cylindrical cell. Step 2. Cell assembly for cylindrical cells. Slide 2 of 2 in this step, the finished jelly roll is inserted into a cylindrical metal can, where tab shaping and canning are completed. The anode tab is bent down and welded to the bottom of the can, while the straight cathode tab is welded to the top, so the can and cap become the negative and positive terminals. The jelly roll is then mechanically fixed in place by beating around the can. Next, under vacuum, the correct amount of electrolyte is injected to fully penetrate the pores of the electrodes. Once wetting is complete, the top cap is crimped to hermetically seal the cell, and an insulated tube is added to prevent short circuits between the can and external connections. Step 3. Formation. Slide 1 of 2. On this slide, we move from mechanical assembly to giving the cell its electrochemical personality. During formation, the cell is charged and discharged under carefully controlled conditions, allowing a thin solid electrolyte interface, or SEI, to form on the anode surface. This SEI layer is created by a small, intentional decomposition of the electrolyte, and it then acts as a protective barrier. It blocks further electrolyte breakdown while still allowing lithium ions to pass. In practice, SEI behaves like an internal separator for electrons, helping to stabilize the chemistry, extend cycle life, and improve safety and performance. We will continue this explanation on the next slide, where we look at aging, degassing, and final quality control. Step 3. Formation. Slide 2 of 2. After the initial charge-discharge cycles, the cells enter an aging period where they rest at a controlled temperature so the electrolyte can fully penetrate the electrodes and the SEI layer can stabilize. In this simplified view, the soaking time, typically ranging from tens of minutes to a few hours, ensures that lithium ions can move smoothly between anode and cathode. In pouch cells, repeated charging, discharging, and aging generate gas within the pouch, so a separate degassing step is used to remove the gas before final sealing. Once the electrochemistry is stabilized and any gas is removed, the cells go through quality control tests, where capacity, internal resistance, and other parameters are checked and underperforming cells are rejected. This slide closes the formation stage and prepares the cells for final pack integration. On step 4, pack process slide 1 of 2, we move from individual cells to modules. After formation, the cell surfaces are cleaned, and the cells are connected cell to cell, usually in series and/or parallel, to reach the required voltage and capacity. These connected cells are then placed into a module case, fixed with adhesive, and linked by a wiring harness or bus bar so current can flow safely and evenly. Once the cover is installed, the module is structurally complete and ready for final pack assembly, which we will see on the next slide. Step 4 for pack process slide 2 of 2. Here, we complete the transition from modules to a functional battery pack. Multiple modules are placed in a single pack housing and interconnected, with the exact number of cells and modules tailored to the application's required voltage, energy, and power. Once the pack is assembled, a battery management system, BMS, is applied to monitor key parameters such as state of charge, temperature, and overall health. The BMS, especially its cell monitoring units, balances individual cells, protects against abuse conditions, and helps the pack operate safely while maximizing usable life.